Hello, everyone. Let's talk about mission number 1, at least 2 types of music. So let's suppose that we have 3 teams of students, and this is in part 2 of the meeting where you're planning your table. So let's say you made these 3 teams of students, and the teams picked these 3 ends. Team 1 picked 2, team 2 picked 6, and team 3 picked 3. So team A chose a risky strategy. Team B was very conservative, just in case. And team 3 or C, well, yeah, was in between. A bit of risk, but less than team A or team 1. Let's suppose that these were the outcomes for each team. So let's say that when drawing, team 1 drew AA, team 2 BBA, CAB, and team 3 AAB. So team 1 fails the mission because they don't get 2 types of music. Whereas team 2 and team 3 both pass the mission, so both get 1 point. But between team 2 and team 3 picked a better end, so least it's smaller, so they get an extra point. So that's how it would go for this round. Now comes the mathematical discussion. You start with this question: what's the least end to make sure we'll pass, and why? So maybe that already happened in part 1. That question was answered, but now you can support more your students and make sure that they really understand. If everybody understands, you can go faster in this part. So the solution is 14, because the words is really that we all pick of the same type and just 1. And the bigger of this is A. So the words is that the first 13 rows is A. And then draw number 14 has to be different. So we will pass the mission no matter what. If we pick 14 songs, knowing that this is much higher than these teams. So it's highly likely that even below 14 songs, maybe the 3rd or the 4th song, it's already a different type, already fulfills the mission. But if we want 100% exact total certainty, we need to pick 14 songs. So this is really, really important to stress out the difference between highly, highly likely and 100% sure, totally secure. Close to 80%. So we don't expect students to derive formulas for probabilities because these are rather kind of time-consuming and hard. So this is not the focus of the meeting, but we want to use their intuition. So for example, they get like this: n equals 1, it's 0% chance. N equals 14 is 100% chance. If the probabilities increase linearly, which is not true, but it's a good initial assumption, then each increase of n would be 7% or so. So maybe they can test n equals 8 or n equals 5, whichever. Let's say they test n equals 5 to start, and they play 20 times. They get 1 fail and 19 passes, 95%. So this is experimental probability. This is not a real probability, but it's an approximation, like a likely value from the observations. So 95 is much bigger than 80, so maybe they pick n equals 4. They still get 95 or so it's lower, and maybe at the end they test again and they conclude n equals 3. You can reveal that n equals 3 gives you the best, the closest to 80%. And so here's the graph that you show them in this part. You show them, well, after doing which is the correct one, which is the real one, you'll end up showing students this graph or revealing that this is the real graph of probabilities. What does this mean? Well, in the horizontal bar space or axis, we see the values of n that we could pick up to 25, but really, let's say here we show up to 20 or 23, doesn't really matter much. And then the length or height of each bar is how likely you are to pass the mission when you stick to this n. Of course, n equals 1 gives you 0 probability, 0%, because you cannot get 2 types of music by just selecting 1 song. But if you select 2 songs, it's more than half likely that you get it done, that you pass the mission. It's actually 66% or so. If you bump to n equals 3, so just 1 more song in your playlist, you jump all the way up to 86% or so. And then you get closer and closer to 99.999%. And then we saw when you hit 15, doesn't seem in the graph, right? Because now it's very close to 1, but actually when you hit 14, as we saw, this is when you get to exactly 100%. Here you see it in this chart. So also it's really important to discuss this feature of highly likely versus totally sure that happens here in the table, because the graph doesn't really get you this, right? Because it looks very, very close. You would have to like zoom in with a magnifying glass to see when it reaches perfect score of 100% at 14. So n equals 1, sure failure, n bigger than 3 is like sure success. N equals 2 is likely to succeed, but pretty risky in a sense if you just play it once. N equals 3 is much less risky. And n equals 6 is low and almost certain. So it seems like a great number to pick if you want to pass the missions, right? But that's not the end of the story. So now you tell students, hey, what do we do with these probabilities, right? So this is a value, a table somehow, or a data that shows all the probabilities. Now we have perfect information. We have the complete picture and knowledge or how likely we are to win each round. But it's not just about winning the round or passing the mission, but winning the round by maximizing your score, right? Meaning you beat all of the other players. So these are good questions to ask. N equals 2 versus n equals 3. Because students may say, oh, I'm going to pick n equals 2. Others say, no, that's too risky. I'm going to pick n equals 3. Others will maybe lean towards picking n equals 10 or 9. And it's fun because when do you stop, right? They're very close. Where do you cut? Where are you satisfied with highly likely? Okay. So here's what you could do. Let's have them discuss n equals 2 versus n equals 3, which is a better strategy. So this would go like this. Suppose we played 100 games. That's some prompt you could tell your students. What would happen if you played 100 games? So it's convenient to start from the n that's lowest, because that's going to win automatically if they pass the mission, right? Regardless of what happens to the other n. So if we play 100 games, the maximum score, of course, is 200, because it's twice that. So what happens to the n equals 2 team? In about 67 games, because it has this probability of, right, of passing. So in about 67 of these 100 games, they will get 2 points, because they're going to pass the mission, and 2 is always less than 3. So they're going to get 2 points. In other words, they get either 0 points or 2 points. In the other 33 games or so, they'll get 0 points. They don't pass. That's what's expected. So if you just duplicate double these 67, you'll get this value, right? So 134 points. That's what we expect them to make, which is quite a lot, right? It's more than half of the maximum, right? What happens to the n equals 3 team? So in these 67 games, they don't even need to play. They will need to play, but they won't get 2 points. So they only get 0 or 1. And it's independent. They play with their own set of songs. So what's expected is that they apply this 86 multiplier, the probability. So 0.86 times 67, that's about 58 points. So what we're saying here is out of these 67 games, they'll win about 58 of those, and that gives them only 1 point. In the other 33, namely those that the other team lost, they'll win not all of them, but this multiplier, right? And then they'll win 2 points because the other team lost. So when you do the math, that's 57. So anyways, it gets less. So the bottom line is that if you just play with two players, n equals 2 versus n equals 3, n equals 2 is expected to win. And by quite good, yeah, good margin, one would say. What happens between n equals 2 versus n equals 10? It's the same idea. So n equals 2, it's exactly the same score. But I don't even have to look at what the other player does. And n equals 10 gets, yeah, it gets interesting because in these 67 games, this multiplier is very close to 100%. So it's like if we had a one pragmatically here when we do the approximations. So they'll get 60 points in those. But then in the other 33, again, this is like a one, this multiplier. They'll get 2 points for each, and they'll win all of them, probably. So that's 66 points. So when you sum, when you add these two, you get practically the same value here. We were approximating here, there. So it's just a toss-up. It's really a tie, like statistically speaking. So n equals 2 versus n equals 10. So 2 beats 3, 2 and 10 tie. So the interesting question now is what happens 3 versus 10. And doing a similar argument, you would say that in about 86 games of this n equals 3, they'll win. This team will win 2 points. So that's quite a lot here. And then the n equals 10 here will get 1 point in these 86 games. And in the other 14, that they'll pass the mission almost for sure, right? Because of what we said, they'll get 2 points. So that's a 28. So when you add this, you're very far. So n equals 3 is expected to win and really, really beat n equals 10. So much more than, yeah. So it's really funny and interesting because n equals this is 2-player game only when we compare. N equals 2 beats n equals 3. So you would prefer n equals 2 here. N equals 3 beats n equals 10. And really beats it, like, yeah, like super, as we said here, like by a lot. So you would expect that transitivity, of course, right? Intuitively, that if n equals 2 beats n equals 3, like a tournament, and n equals 3 beats n equals 10 again, then n equals 2 would beat n equals 10. But what we saw is that it's a tie here. So this may motivate your students and yourself into this interesting thing. If you have time, I encourage you to simulate or think about it. A 3-player game between this n equals 2, n equals 3, and n equals 10. Use the same logic to see who beats which team beats other teams and by how much, how many points the differential. Okay, so hopefully this helps and you get to at least some of these discussions. So it's not about computing probabilities, it's more about understanding what this means, how to interpret this. But it's not just to explain what it means and end of the story, but how are we going to use it in the context of the game? Okay, I know these values. How does this help me in choosing the end? And again, there's going to be probably 3 boats, 3 sides of the story or 3 student types. One that will claim that this is n equals 2, it's the best choice just because it's above 500% and it's really small. Other students that disagree and that is too risky and they rather have maybe n equals 3 or 4. And other types of students that said that maybe n equals 7 or 8 is the best. And this is just the tip of the iceberg or what you could do. Of course, you won't have much time, so I don't expect you to go beyond maybe these considerations. But that's what you do. You start talking about how would we play 100 games? What if we play 1,000,000 games? this versus these two players, what happens? What's the best strategy? Here we saw that, and this in this picture, that n equals 2 is solid, right? From many points of view. It doesn't win all games because it ties with n equals 10, but thus far it hasn't lost any. So that's another question you could ask. Is there a game situation? In other words, have these many players and these values of n in which n equals 2 is bad. So it's not convenient at all, and you would rather choose other values. And if so, try to find. And if not, if n equals 2 is really solid, try to explain what numerically or reason abstractly. Okay, you have a lot of fun, and see you in another video. Goodbye.